Hope you're having a productive day. In this video, we will be going through a question from a physics past paper 2. It will be question number 1 from the 2014 paper. So let's get right into it. First thing the question gives is an image. It says figure 1 shows a missile fired from the ground with a velocity of 300 meters per second at an angle of inclination of 40 degrees. The missile is in flight for 39 seconds. Part 1 of Part A asks you to calculate the initial horizontal component of the missile's velocity, and Part 2 of Part A says, by neglecting air resistance, determine the horizontal range of the missile. In order to find the horizontal component of the missile's velocity, let us do a quick sketch. This is a level plane from which the missile is being fired from, and this is the missile's initial velocity. This is stated to be 300 meters per second. The angle is stated to be 40 degrees. Now you're trying to find the horizontal component of this velocity here. In order to find that, you're basically trying to find this component down here of the horizontal velocity. We have an angle and we have two sides, and this can form a right angle triangle if I put a line here. So basically what that means is you have an angle and you have the hypotenuse and you have the adjacent. Cos theta is equivalent to the adjacent side, which in this instance would be the initial horizontal component, and you have the hypotenuse, which would be 300, which would be that. So all you have to do to find the initial horizontal component is to multiply cos of the angle by 300 meters per second. When you do that, you should get an answer of 229.8 meters per second. So that's the initial part solved. The question then asks you to determine the horizontal range of the missile. Because the question said to disregard air resistance, it's basically telling us that the only force acting on the missile is gravity. If the only force acting on the missile is gravity, then the missile's X movement, or the X component of the missile, is not being affected by any force. And because it's not being affected by any force, that means there is no acceleration in the X direction. And that means, it's a long explanation, I know, but that means that the initial velocity is basically the same as the final velocity. The question gave us time, so with time, we should be able to find the range or the distance in the X direction. And we can use this formula here. Average velocity is equivalent to displacement divided by time. Now, average velocity, like I said, is going to be the same as this velocity here because the velocity doesn't change. The final and initial velocities are the same, so the average velocity is just this. And then all we have to do to find the range, which is d, or displacement, is multiply both sides by time. And we should get d is equivalent to this component of the velocity, which was 229.8 meters per second times time. Now the question gave us time. The question gave us time as 39 seconds. The missile is in flight for 39 seconds. We're going to multiply the 229.8 meters per second by 39 seconds. And because this is per second and this is seconds, they cancel out. Per second means 1 divided by second, and second is just second divided by 1. So 1 divided by second multiplied by second divided by 1 is going to give you, well, 1. To show it, 1 divided by a second times a second divided by 1. The seconds cancel, and you're left with 1. So the seconds cancel, and that's why they cancel. Most of the times you're working with physics, the units that you have for your variables will work out to give you the units for the final answer. So here we get the final answer to be 8,962 meters or approximately 8.962 kilometers if you wanted to do the conversion. So that's the second part of the question answered. Let us move on to part B of the question. Figure 2, comprising 6 pictures labeled 1 to 6, represents a series of snapshots of a rubber ball in motion. The ball was raised from the floor to a table of height 1.7 meters. It was then dropped from the table onto the floor and bounced up 1 meter. Then it gives you some questions. In which picture does the ball have maximum potential energy? In which picture does the ball have maximum kinetic energy? And how much potential energy has the ball lost from picture 1 to picture 6 if the ball weighs 2 newtons? So after familiarizing yourself with the question, you can get into answering it. The first 2 parts of part B don't require much calculation, but having a formula can help answer these 2 questions. Fast drivers. So basically, it asks, in which picture does the ball have maximum potential energy? Let us write the formula for potential energy. Let us write the formula for gravitational potential energy. That formula is basically mass times gravitational field strength times height. Now this is the formula for gravitational potential energy. Throughout all the pictures, the mass of the ball is constant, so that doesn't change. The gravitational field strength of the ball would not change a lot because a distance or a height of 1.7 meters above the ground of the Earth is not large enough a distance for the gravitational field strength to vary too much. So basically the gravitational field strength is more or less constant. What changes is the height. So which one of these heights would give us the most potential energy? Well, it stands to reason that the height that is largest gives us the largest potential energy since height is being multiplied by these other 2 variables. If these 2 variables were being divided by height, then you would have a different story. But since height is in the numerator of this, then the largest height gives the most potential energy. So which one of these pictures is the ball at the highest height? It is indeed picture 1. So that is the picture where the ball has maximum potential energy. Now we move on to the second part. In which picture does the ball have maximum kinetic energy? Now gravity is a conservative force because the path taken does not affect the work that is done. And when dealing with conservative forces, the total mechanical energy of the system remains constant, which means that the change in potential energy must be equated to an equal change in kinetic energy. So when the kinetic energy is highest, the potential energy is lowest. Which one of these has the lowest potential energy? Well, it is the one where the height is lowest. According to that formula right there, we want this height to be small. And when this height is small, potential energy is small. When the potential energy is small, there was a difference in potential energy, and that difference in potential energy is going to be equivalent to the increase in kinetic energy. So where is the height the smallest? The height is the smallest in 4, meaning that the potential energy is lowest in 4 and the kinetic energy is highest in 4. So that is the picture that gives you the most kinetic energy, or the picture in which the ball has the most kinetic energy. Now we have to do a small calculation. How much potential energy has the ball lost from picture 1 to picture 6 if the ball weighs 2 newtons? Well, change in potential energy would be the difference between potential energy. So that would basically be mg h2 minus h1. Now, the difference in height between h2 and h1 is indeed 0.7 meters. So it would be mg times 0.7 or mg times negative 0.7. mg is the same as weight, which they stated was 2 newtons. So we multiply 2 newtons by negative 0.7 meters, and we arrive at our final answer, which is, when you multiply the 2 newtons times negative 0.7 meters, you end up with negative 1.4 joules. Remember the units. It's negative because the potential energy has been lost. But if they're just asking for the magnitude of the energy loss, then you could ignore the negative sign and just write 1.4. joules. Part C gives us a table and it wants us to plot a graph. Table 1 records the results of an experiment to determine the relationship between rebound height, h rebound, and maximum height before rebound, h before. On the grid provided on page 7, plot a graph of h rebound versus h before starting at the origin. Use the graph in C above to deduce the equation relating h rebound to h before, and then how high would the ball be expected to rebound if it were dropped from a height of 2.04 meters. So part C wants us to do three things. Number one, it wants us to plot a graph. Number two, it wants us to determine an equation from the graph. And number three, it wants us to use that equation to get a value based on 2.04 maximum height before rebound. When you're plotting graphs, you have to ensure that you use a suitable scale that will allow all of the values on that scale to fit in quite comfortably. Now, for instance, h before is going to be plotted on the x-axis since it's mentioned second here. So h before is going to be plotted on the x-axis. So our x-axis has to hold all of this information. So we start from 0 and we go up to approximately about 2 meters. Now, we need to find a scale that can fit those 2 meters with divisions in between to show that the graph is still big and show all the different points. So in order to do that, you start with your graph. Now let's say this distance between here and here on the graph paper was 10 centimeters. It means that you need to fit the numbers from 0 to 2 in 10 spaces. This basically means that 1 centimeter would be equivalent to 0.2 of the actual units that are going on the axis. So basically, if you have units that go from 0 to 2 and you have 10 divisions, then you could basically say 2 divided by 10 is 1/5. 1/5 as a decimal is 0.2. Each x division is going to represent 0.2 of the unit. You can find other ways of plotting your graph. It just takes practice, but this could probably help you to plot a graph a little bit faster. So basically, I'm just going to populate this graph and then plot the points. So these are the divisions that we eventually get for our graph. Now, it is important to note that for your graph, you have the axes labeled properly. So this is the x-axis. And this is the y-axis. And then you're also going to ensure that the numbers are present on all these. So this number would be 0.1. This would be 0.2, 0.3, 0.4, 0.5. So you're going to include all of the numbers. I'm not going to include all of them because I don't have the space for it. So those would be some of the numbers that you would have. And of course, you have your 0 here, where your graph starts from. And you're going to do the same thing for down here. You're going to put all the numbers in. And you are also going to name both axes. The y-axis from the question was supposed to be h rebound, and the x-axis on the question is supposed to be h before. So on your graph, you would put h rebound and you would put h before. And you would also put the units for those two labels. Now, when you've put your axes, you've put in your numbers, you've written the name of each axis, you also need to ensure that your graph has a title, which is going to be the y variable versus the x variable. You also have to include a scale for your y-axis and your x-axis. So you're going to work out basically how much 1 centimeter on each axis represents the actual values that are on them. In this instance, if this was 1 centimeter here, 1 centimeter would represent 0.1 meters for the x-axis, and it would do the same for the y-axis since 1 centimeter is 0.1 here. So you also have to ensure that you include your scales, What else? So you have your title, you have the names, you have the label of the axes, you have the numbers, you have your scale. You also have to plot the points on the graph and then draw a best fit line through those points on the graph. Allow me to plot the points real quick. So this is what my graph looks like roughly when all the points have been plotted. Now you have to draw your best fit line. So in this question, it said the line should start at the origin. So it's going to start like that, and it's going to pass through as many points as possible. So something like this would be a best fit line. So it passes through these 2 points directly, and it has this point above it and these points below it, so it goes in between those 2 points as well. So once you've gotten your best fit line drawn and your graph is complete, you should be able to get the marks for your graph. But we're not done with the graph just yet. It says use the graph in C above to deduce the equation relating H rebound and H before. Now H rebound is over here and H before is down here. So when you have a straight line like this, it basically means whatever is on the y-axis is proportional to whatever is on the x-axis. So basically we get y is directly proportional to x. And that basically means that we can replace the proportionality sign with a constant. So it means y is equal to a constant times x. Now if your graph is a straight line and it passes through the origin, then it basically means that this k is m, and m is just the gradient of the graph. So this is basically y is equal to mx. So whatever is on the y-axis, H rebound, is equal to m, which is the gradient, times x, or whatever is on the x-axis, which is H before. All you need to do now is just solve the gradient and plug it in to this formula, and you will get the final equation that you need. In order to find the gradient, you're going to take 2 points from the graph. Say for instance this point here. You're going to take this point here and you're going to make a triangle. You carry this point down and then you make a triangle with the rest of the graph. And it's recommended that this triangle is large, and I also think it should not be one of the plotted points on the graph either. So this triangle is large, and as you can see, it's not one of the plotted points on the graph. The gradient is basically equivalent to the change in y, y2 minus y1, divided by the change in x, x2 minus x1. Or if some people say the rise over the run. So I've drawn a big triangle here, and you can read off the y values by coming here and reading there and doing the same down here. And you can read the x values by coming here, reading down, and you read down from there. So the y value for this is approximately, this is 0.9, so this is going to be 1, and this is going to be 1.1, so about 1.1, maybe 1.16. Doesn't have to be too accurate. So we're going to get 1.16 meters, and then y1 would be the y value down here. So this would be approximately 0.1 0.16. And then the x values would be 2 minus the initial, or the smaller one, x1, which would be about 0.1, so it would be approximately 0.21. So we're gonna work this out, and when we work it out, we get 0.56. And this does not have any units, because as you can see right here, where you have meters subtracting meters, you would end up with meters here. And then here, when you have meters subtracting meters, you would end up with meters in the denominator as well. And then meter up top, meter at the bottom, they cancel out to give 1. And therefore, the gradient does not have any units in this scenario. So the equation that we would need would be H rebound is equivalent to 0.56 H max. The last thing that is asked of us is to find how high would the ball be expected to rebound if it were dropped from a height of 2.04 meters. To do that, you simply just come back to this equation. So they're trying to find HR, which is the rebound height. So the rebound height would be 0.56 times the height before, the maximum height before, which would be maximum height before, which would be 2.04 meters. And that would equate to 1.14 meters. And that would be the end of the question. So if you did all of this, where you did the working out and the graph, and you did the gradient of the graph, and then you plug the gradient in to give you the equation of the graph, and then you get a value, and then you find the value of H rebound when giving a value of H before, then you would get 15 marks for doing all of this. That's going to be the end of this past paper questions video. Thank you all for watching, and I hope you've learned something.